Every electron in the universe carries exactly the same electric charge. Not roughly the same, exactly the same. The electron in your fingertip, the electron buried inside a distant star, the electron that flickered into existence in a collision a billionth of a second ago, every single one carries an identical sliver of negative charge, matched to a precision almost beyond belief. And here's the unsettling part. We can measure that charge with staggering accuracy. We can predict how it behaves to 11 decimal places, better than almost anything else in all of science. But ask the simplest question of all. Where does the electron actually get its charge? Why does it have that precise value? And what is charge even made of? And physics falls quiet. There is no confirmed answer. Tonight, we walk straight into a mystery hiding inside something you first learned about as a child. If these kinds of deep questions are the sort of thing you enjoy chasing, a quick like or subscribe genuinely helps this channel keep going. It only takes a second for you, but it means a lot for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Hold a single thought in your mind for a moment. There is a particle inside every atom of your body, inside every atom of the chair you are sitting in, inside the screen you are looking at right now. It is called the electron, and it carries a property we call electric charge. That property has a specific value, and that value is the same, not similar, not close, but exactly the same, for every electron that has ever existed, anywhere in the entire history of the universe. Think about how strange that statement really is. There are more electrons in a single drop of water than grains of sand on all of Earth's beaches. There are electrons in the heart of the sun, electrons drifting in the cold emptiness between galaxies, electrons that were created in the first fraction of a second after the universe began, and electrons that blinked into existence a heartbeat ago in a laboratory on Earth. Not one of them carries a slightly larger charge. Not one of them carries a slightly smaller charge. Every last one is identical, matched to a precision so extreme that experiments have never found even the tiniest deviation. And here is the question that physics, for all its triumphs, still cannot answer. Where does that charge come from? Why does the electron have exactly the amount it has, rather than a little more or a little less? What, at the deepest level, is electric charge actually made of? You might assume these questions were settled long ago. Electricity is old news after all. We light our cities with it. We run our entire civilization on it. We learned about positive and negative charges in school as children. Surely something so familiar, something so thoroughly tamed, must be fully understood by now. But it is not. And the gap between how well we can measure charge and how poorly we can explain it is one of the quietest, most overlooked mysteries in all of science. We can predict the behavior of a charged electron to 11 decimal places. We can build technologies of unimaginable precision around it. Yet when you ask the most basic question, why does charge exist and why this exact value? The honest answer is that nobody knows. To understand the mystery, we first have to understand what charge actually is in the modern picture of physics. And to do that, we need to throw out a very old and very tempting idea. Most people imagine electric charge as a kind of substance, a glowing stuff, a fuel that sits inside the electron, like water inside a balloon, that can leak out, get used up, or be poured from one place to another. This picture feels natural. We talk about charging a phone, about a battery running out of charge, about static electricity building up and then discharging in a spark. The language itself encourages us to think of charge as something that flows and drains and refills, but that picture is wrong, or at least deeply misleading. Charge is not a substance the electron contains. The electron does not have a little tank of charge inside it that could one day run dry. When lightning leaps from a cloud, no charge has been created or consumed. Charge, as far as we have ever been able to determine, can be neither created nor destroyed. The total amount of it in any isolated system stays exactly constant, forever. This is one of the most rigorously tested laws in all of physics, and it is called the conservation of charge. So if charge is not a substance, what is it? In the language of modern physics, charge is a property. More specifically, it is the single number that determines how strongly a particle interacts with the electromagnetic field. That is the whole of it. That is what charge is. It is not a thing, it is a relationship. It is the measure of how tightly the electromagnetic field can grip a particle, and how forcefully that particle can push back on the field in return. Let me unpack what that means, because the idea of a field is central to everything that follows. In the older way of thinking, going back centuries, forces acted at a distance. The Earth pulled on the Moon across empty space. A magnet pulled on a nail across an empty gap. Two charged objects pushed or pulled on each other with nothing in between. This troubled physicists deeply. How can one object reach across emptiness and affect another with nothing connecting them? It seemed almost like magic. The resolution, developed across the 1800s and refined ever since, was the concept of the field. Instead of acting across empty space, a charged particle fills the space around it with an invisible influence, the electromagnetic field. This field stretches out in every direction, growing weaker with distance but never quite vanishing. When a second charged particle enters that field, it feels a push or a pull. The two particles never touch. They never reach across the gap directly. Instead, each one talks to the field, and the field carries the conversation between them. Picture a vast, invisible, jelly-like substance filling all of space. It is everywhere, in the room you are in the depths of space, threaded through the atoms of your own hand. This is the electromagnetic field, and in modern physics it is just as real as matter itself. A charged particle is a disturbance in this field, a knot of energy that both responds to the field and reshapes it. And the amount of charge a particle carries is precisely the strength of its connection to that field. It is the volume knob on the conversation. Turn it up, and the particle shouts at the field and listens loudly in return. Turn it down, and the particle barely whispers. This is why charge is best understood as a coupling. The word coupling means a connection, a linkage, a binding together of two things. The electron's charge is the strength of its coupling to the electromagnetic field. A particle with no charge at all, and there are such particles, simply does not feel the electromagnetic field. The field passes through it as if it were not there. Light, which is itself a ripple in the electromagnetic field, can wash over an uncharged particle without nudging it in the slightest. But a charged particle is woven into that field. It cannot ignore it. It feels every ripple, every wave, every disturbance, and it sends out disturbances of its own. So the electron's charge controls one specific, profound thing: how the electron and the electromagnetic field talk to each other. That is what charge does. And from that single fact, an astonishing cascade of consequences flows. Consequences that build atoms, ignite chemistry, power electricity, and fill the universe with light. But we will come to all of that. For now, hold on to the core idea. Charge is the handle by which the electromagnetic field grips the electron. Nothing more and nothing less. Now, let us return to the mystery, because defining charge only sharpens it. We have said that the electron's charge is the strength of its coupling to the field. Fine, but why is that strength what it is? Why does the electron couple to the field with exactly the firmness it does, and not a touch more firmly or a touch more weakly? To even ask this question properly, we need a number. Physicists have measured the electron's charge with extraordinary care, and they express it in a unit called the coulomb, named after a French scientist who studied electric forces. The charge on a single electron is about 1.602 times 10 to the negative 19 coulombs. Written out, that is a decimal point followed by 18 zeros before you reach the meaningful digits. It is an almost unimaginably small amount of charge by everyday standards. To gather up one full coulomb of charge, you would need to round up roughly 6 billion electrons. That is 6 followed by 18 zeros of them. But the smallness of the number is not the point. The point is its exactness and its universality. Every electron carries that identical value, and the negative sign in front of it, because the electron's charge is, by convention, negative, is also identical. There are no slightly more negative electrons. There are no slightly less negative electrons. They are clones of one another in this one respect, perfect copies stamped out by some process we do not understand, scattered across all of space and all of time. This is genuinely bizarre when you sit with it. Imagine if every grain of sand on every beach on Earth weighed precisely the same to 40 decimal places. Imagine if every raindrop that had ever fallen contained exactly the same number of water molecules, with no exceptions, ever. You would immediately suspect that something deep was going on, some hidden machinery enforcing that perfect sameness. Yet that is exactly the situation with the electron's charge, and physics has no confirmed account of the machinery. Now, it would be easy to assume that the standard model of particle physics, our best, most successful theory of the fundamental particles and forces, explains this. The standard model is one of the great achievements of human thought. It describes the electron, the quarks that make up protons and neutrons, the particles that carry the forces, and far more besides. It has been tested in thousands of experiments and has passed every one, often to breathtaking precision. Surely such a theory tells us where charge comes from. But here is the uncomfortable truth. The standard model does not explain the electron's charge. It assumes it. The value of the charge is not something the theory predicts or derives from deeper principles. It is something physicists measured in the laboratory and then fed into the theory by hand. The standard model takes the electron's charge as a given, as one of a handful of input numbers that the universe simply hands us, with no explanation attached. The theory is magnificent at telling us what charged particles will do. It is silent on why charge has the value it does in the first place. Physicists have a name for numbers like this. They call them free parameters, or fundamental constants. They are the dials of the universe, the settings that have to be measured rather than calculated. The electron's charge is one of these dials. We know its position with extraordinary accuracy. We have no idea who or what set it there. Let me make the strangeness of this even clearer with an analogy. Suppose you found a machine of incredible sophistication, a vast, intricate device with millions of moving parts, performing complex tasks flawlessly. You study it for years. You map out exactly how every gear meshes with every other gear, how every signal flows, how every output depends on every input. But there is one thing you cannot explain. On the side of the machine sits a single dial, and that dial is set to a particular value. The entire behavior of the machine depends on that setting. Yet nothing inside the machine determines where the dial points. It was simply set there before you ever arrived, by hands you never saw. You can see the dial, you cannot explain it. That dial is the electron's charge. The machine is the universe. And we are the bewildered investigators who understand everything except the setting that makes it all work. You might wonder whether the value is just arbitrary, whether the universe could have had any charge it liked, and this one is no more meaningful than a random roll of dice. But that possibility is, if anything, more disturbing, because the exact value of the electron's charge turns out to be woven into the very possibility of our existence. If the strength of the electromagnetic coupling were significantly different, atoms would not hold together the way they do. Chemistry as we know it would not exist. Stars would burn differently, or perhaps not at all. The delicate balance that allows complex structures, molecules, cells, planets, people, to form depends on the electromagnetic force having roughly the strength it has. Change the dial much, and you change the universe into something that could not contain you. So we are left with a number that is, simultaneously, perfectly measured, perfectly universal, deeply consequential, and completely unexplained. That combination is what makes the electron's charge one of the most fascinating puzzles in physics. Let us be careful, though, about what kind of puzzle this is. It is tempting to imagine that the answer is just around the corner, that some clever physicist will soon crack open the electron, peer inside, and find the gears that generate its charge. But the situation is more subtle than that. As far as every experiment has ever been able to tell, the electron has no inside. It appears to be a true point, a particle with no size, no internal parts, no smaller pieces rattling around within it. We will explore that strange fact more deeply later. For now, simply notice what it implies. If the electron has no internal structure, then its charge is not generated by some mechanism hidden inside it. The charge is not the sum of smaller charges. It is not produced by tiny spinning components or internal currents. It is, as far as we can tell, simply an intrinsic property, a feature the electron possesses in and of itself, woven into what it fundamentally is. The word intrinsic is important. It means belonging to the thing by its very nature, not added on, not assembled, not derived from parts. The electron's charge is intrinsic in exactly this sense. It is not something the electron has acquired. It is part of the electron's identity. To be an electron just is, among other things, to carry this particular charge coupling to the electromagnetic field. Strip the charge away, and you would no longer have an electron at all. You would have something else entirely. This is a profound shift from the way we usually think about properties. When we say a brick is heavy, we understand that its heaviness comes from the matter packed inside it, from the atoms and their arrangement. The heaviness is built up from smaller things. But the electron's charge is not built up from anything. It does not come from smaller charged pieces, because there are no smaller pieces. It is a bedrock property, a starting point rather than a result. And this is part of why the question of its origin is so hard. We are used to explaining properties by breaking things down into their components. But you cannot break down a point. There is nothing smaller to appeal to. Now, you might reasonably ask, if the electron is just a point with no parts, how can it carry a property at all? How can something with no size, no internal structure, no inside, possess a charge? This is one of those questions where our everyday intuitions, built up from a lifetime of handling ordinary objects, simply fail us. In the world we evolved to understand, properties live in things, and things have insides where their properties can reside. But the electron is not an ordinary object. In modern physics, it is best understood not as a tiny ball at all, but as an excitation, a ripple, a vibration, in a deeper field of its own. Just as the electromagnetic field fills all of space, there is also an electron field filling all of space, and what we call an electron is a particular kind of disturbance in that field. The charge is a property of that disturbance, a feature of the way the electron field connects to the electromagnetic field. The charge does not sit inside a ball. It describes a relationship between fields. This is admittedly a slippery picture, and if it feels difficult to grasp, that is entirely appropriate. We are at the edge of where human intuition can comfortably travel. The crucial takeaway is this: the electron's charge is real, it is precisely measurable, it governs how the electron and the electromagnetic field influence each other, and yet it is not made of smaller charged ingredients. It is fundamental. It is a flaw we have not been able to dig beneath. And the precision of our measurements only deepens the irony. We have weighed the electron's charge against itself, so to speak, with such delicacy that we can detect changes that would correspond to differences in the 11th or 12th decimal place. We compare the charge of the electron to the charge of the proton, its mirror image partner in the atom, and find them equal and opposite to a staggering degree of accuracy. We watch electrons in atoms, in beams, in collisions, and their charge never wavers, never drifts, never shows the slightest variation. By almost any standard, electric charge is among the best understood quantities in all of science. We know it more precisely than we know the age of the universe, more precisely than we know the mass of almost anything, more precisely than we know countless quantities we consider thoroughly settled. And yet, ask the simplest question a curious child might ask: but where does it come from? And the magnificent edifice of modern physics has no confirmed reply. We can describe charge with overwhelming success. We cannot explain its origin. We have measured the setting of the dial to extraordinary precision, while remaining utterly ignorant of the hand that set it. This is not a failure of effort. Some of the most brilliant minds in the history of science have wrestled with the foundations of electromagnetism and the nature of charge. It is, rather, a reflection of just how deep this particular question runs. We are not asking a question about the behavior of charged particles, which we understand exquisitely well. We are asking a question about why one of the basic ingredients of reality is the way it is, and questions of that kind sit right at the boundary of what current physics can address. There is something almost humbling in this. We have split the atom, peered back to the first instance of the universe, detected ripples in space-time itself from black holes colliding billions of light years away. We have built theories of astonishing power and precision. And still, the humble electron, the very particle that flows through every wire and lights every screen, the particle we harnessed so thoroughly that we built the modern world on it, keeps a secret it has never given up. It carries a charge whose origin we do not know. In what follows, we are going to take this mystery apart, strand by strand. We will see exactly what that one fixed number accomplishes, how a single intrinsic property, identical across all of existence, reaches out through the electromagnetic field to pull electrons toward protons and bind them into atoms, to push like charges apart, to drive the electric currents that run our civilization, and to shake the field into the waves of light that let you see this very moment. We will confront the strange fact that the electron has no inside, no smaller charged pieces, and ask what it could possibly mean for charge to come in identical, indivisible packets. We will look at the eerie matching between the electron and the proton, two utterly different particles that nonetheless carry charges of precisely equal size. And we will draw a careful line between describing charge, which our theories do superbly, and explaining it, which they do not do at all. But before any of that, let the central fact settle fully into place, because everything else hangs from it. Somewhere in the architecture of reality, there is a number. It governs how the most familiar particle in the universe grips the field that fills all of space. That number is identical for every electron, everywhere, always. We can measure it to a precision that borders on the absurd, and we do not know why it has the value it has, where it comes from, or what, at the deepest level, it truly is. It is one of the most precisely known, yet least understood quantities in the whole of physics, a perfect, universal, unexplained setting on the great machine of the cosmos. That is where our journey begins, with a question hiding in plain sight, inside something you have known about since you were a child, asking patiently to be understood. So far, we have a single fixed number, the strength of the electron's coupling to the electromagnetic field, and a deep mystery about where it comes from. But a number on its own does nothing. To understand why this particular property matters so enormously, we have to watch it work. We have to follow the charge out into the world and see what it builds. And what it builds, once you start tracing the chain, turns out to be almost everything you have ever touched, seen, or experienced. Let us begin with the most basic behavior of all, the one you may have learned as a child. Like charges repel, and opposite charges attract. Bring two electrons close together, and they push apart. Bring an electron near a proton, which carries the opposite charge, and they pull toward each other. This simple rule is the seed from which the entire structure of matter grows, and every bit of it traces back to that one intrinsic coupling we have been discussing. Here is how the attraction and repulsion actually work in the modern picture. Recall that a charged particle does not reach across empty space to touch another. Instead, it disturbs the electromagnetic field around it, and that disturbance carries the influence to other charged particles. When two electrons approach, each one is steeped in the field of the other. Each feels the field pushing on it, and because they carry the same kind of charge, that push drives them apart. When an electron and a proton approach, the opposite kinds of charge mean the field pulls them together instead. The strength of these pushes and pulls depends directly on how much charge each particle carries, which is to say, on that fixed coupling. A particle with no charge feels nothing. A particle with charge feels the full force of the conversation. Notice something crucial here. The force is not something separate from the charge, layered on top of it. The force is what charge does. To have charge is to participate in these attractions and repulsions. The two are inseparable. When we say the electron has a charge, we are saying nothing more and nothing less than that the electron pushes and pulls on other charged things through the electromagnetic field, with a strength set by that one universal number. Now watch what this single behavior accomplishes. Take one proton and one electron. The proton's positive charge and the electron's negative charge attract. The electron is drawn toward the proton. But the electron does not simply crash into the proton and stick. Instead, governed by the strange rules of quantum mechanics, it settles into a kind of standing pattern around the proton, a cloud of probability hovering at a characteristic distance. That arrangement, one electron bound to one proton, is the simplest atom in the universe. It is hydrogen, and it exists because of charge. The attraction that holds the electron to the proton is the electromagnetic attraction, set in strength by the coupling we cannot explain. This is the first great achievement of charge. It builds atoms. Every atom in existence is held together by the electromagnetic attraction between its negatively charged electrons and its positively charged nucleus. The nucleus, packed with protons, carries positive charge. The electrons, drawn by that charge, arrange themselves around it. Without the electromagnetic attraction, there would be no atoms at all. just a thin, cold soup of separate particles drifting forever apart, never assembling into anything. The charge is the glue. It is the reason matter can clump into structured, stable units rather than remaining a featureless haze. Before we follow charge upward into atoms and chemistry, it is worth pausing on the rawest, most visible form of charge you can encounter in everyday life: static electricity. You have felt it. You shuffle across a carpet on a dry day, reach for a metal doorknob, and a tiny spark jumps the gap with a sharp little shock. You pull a sweater over your head and hear it crackle. You rub a balloon on your hair, and the strands stand up and follow it. All of this is charge, made briefly and dramatically visible, and the mechanism behind it tells us something important about how charge moves between objects. Here is what is actually happening. When two different materials are pressed together and rubbed, electrons can be pulled from one material and deposited onto the other. Remember that charge cannot be created or destroyed, so no new charge is made in this process. Instead, charge is transferred. Some of the loosely held electrons in one object are dragged onto the surface of the other. The object that loses electrons is left with fewer negative charges than positive ones, and so it becomes positively charged overall. The object that gains them now has an excess of electrons, and so it becomes negatively charged. Neither object had its charge created from nothing. The electrons simply moved from one place to another, and the imbalance is what we feel. Once an object carries this imbalance, it wants to get rid of it, because like charges repel one another and crowd toward any available escape. The excess electrons push against each other, straining to spread out and leave. When you bring a charged hand near a conducting doorknob, the gap between them becomes a kind of pressure point. If the imbalance is large enough, the charge leaps across the air itself in a sudden rush. And that rush of electrons, briefly heating the air it passes through, is the spark and the snap you feel. The crackle of a sweater, the tiny lightning of a doorknob, and the vast, world-shaking bolt of a thunderstorm are all the same phenomenon at different scales. An accumulated imbalance of charge, discharging as the electrons finally find a path to flow. This points us toward a distinction that runs through everything electrical, and it is one of the most consequential facts about how charge behaves in the materials of the world. In some substances, electrons are free to roam. In others, they are locked tightly in place. We call the first kind conductors and the second kind insulators, and the difference between them is, once again, a story about charge and the electrons that carry it. In a conductor, and metals are the great example, some electrons are only loosely attached to their atoms and can drift through the material with ease. This is the mobile sea of charge we will meet again when we discuss electric current. Because these electrons can move, a conductor allows charge to flow through it and to spread across its surface. That is why a charged object discharges so readily on touching metal. The conductor offers the crowded electrons a path to escape. In an insulator, glass, rubber, plastic, dry wood, air under ordinary conditions, the electrons are held firmly to their atoms and cannot wander. Charge placed on an insulator tends to stay put, stuck where it lands, unable to flow away. This is precisely why a rubbed balloon holds its charge long enough to lift your hair, and why we wrap electrical wires in plastic and rubber. The insulating sheath traps the charge inside the metal where it belongs and keeps it from leaking into your hand. The entire art of controlling electricity, of guiding it where we want it and keeping it away from where we do not, comes down to the careful arrangement of conductors and insulators, of materials that let charge flow and materials that refuse to. And whether a given material does one or the other depends on the behavior of its charged electrons, governed by that same fixed coupling we have been tracing all along. And the specific way electrons arrange themselves around a nucleus, that too flows from charge, working together with the rules of quantum mechanics. Electrons cannot all pile into the same place. They organize into layers, into shells, into a structured architecture around the nucleus. The number of electrons an atom has, and the way they fill these shells, determines everything about how that atom behaves. It determines whether the atom is a metal or a gas, whether it is reactive or inert, whether it will bond eagerly with its neighbors or remain aloof. The entire periodic table of the elements, every distinct kind of atom, from hydrogen to gold to uranium, is, at bottom, a catalogue of different ways that electromagnetic attraction can arrange electrons around nuclei of different sizes. This brings us to chemistry, which is the next great cascade. Chemistry is, in essence, the study of how atoms join together to form molecules. And how do atoms join together? Through their electrons, which is to say, through charge. When two atoms come close, their outer electrons interact. Sometimes electrons are shared between atoms, forming a bond that holds them together. Sometimes an electron is transferred from one atom to another, leaving both atoms electrically lopsided, so that they cling to each other through attraction. Either way, the bonds that build molecules are electromagnetic in nature. They are charge at work. Pause and consider the reach of this. Water is two hydrogen atoms bound to one oxygen atom, bound by charge. The proteins that make up your muscles, the DNA that carries your genetic code, the sugars that fuel your cells, the air you breathe, the stone and metal and wood and plastic of the world around you. All of it is atoms held together by electromagnetic bonds. Every chemical reaction, every act of burning, dissolving, growing, digesting, rusting and decaying is electrons rearranging themselves, charges shifting their allegiances, bonds breaking and reforming. The whole of chemistry, and therefore the whole of biology, since life is chemistry of staggering complexity, rests on the foundation of electric charge. There is one consequence of charge so constant, so ever-present, that we almost never notice it, and yet it is acting on you at this very moment, in every point where your body touches the world. It is the simple fact that solid matter is solid, that the floor holds you up, that your hand does not pass through the table when you rest it there, that objects have surfaces you can press against and feel. All of this, strange as it sounds, is electric charge at work. You might assume that solidity comes from atoms being packed tightly together, hard little pellets jammed against one another with no room to spare. But that picture is almost entirely wrong. An atom, as we have seen, is overwhelmingly empty space, a tiny, dense nucleus with a thin cloud of electrons spread out at a relatively enormous distance and vast emptiness in between. If solidity came from atoms physically filling space, matter would hardly be solid at all, because there is so little actual stuff in any atom. The hardness of the world does not come from atoms touching, it comes from charge. When you press your hand against a table, the electrons in the outermost layer of your skin approach the electrons in the outermost layer of the table's surface, and electrons, carrying the same kind of charge, repel one another. As the two surfaces are pushed together, this repulsion grows stronger and stronger, resisting the approach, pushing back against your hand with exactly the force needed to stop it. Your hand never actually touches the table in any direct sense. The electrons of one never meet the electrons of the other. What stops your hand is the electromagnetic repulsion between the charges in the two surfaces, an invisible cushion of pure force, holding the atoms of your skin a tiny distance away from the atoms of the table. This is true of every contact you have ever made with the physical world. When you sit in a chair, the charge in the chair pushes back against the charge in you, and that repulsion is what holds you up against gravity. When you grip a handle, when you walk across the ground, When you feel the texture of any surface beneath your fingertips, you are feeling charge repelling charge. The entire sensation of solidity, the resistance, the firmness, the very impossibility of two objects occupying the same space is the electromagnetic repulsion of like charges made tangible. Matter feels solid not because it is full, but because it is charged. Take away that repulsion, and the apparent solidity of the world would simply vanish, leaving only the near emptiness that atoms truly are. So already, from this one fixed property of one tiny particle, we have built atoms, the periodic table, chemistry, molecules, and ultimately, life itself. And we are only getting started. Let us turn now to something that may feel more obviously electrical: electricity itself. The very word comes from the Greek for amber, because the ancients noticed that rubbing amber could make it attract small objects, an early, mysterious hint of charge at play. But the electricity that powers your home is charge doing something more dynamic. It is charge in motion. Inside a metal wire, something special is happening. In most materials, electrons are tightly bound to their atoms, locked in place. But in metals, some of the electrons are loosely held. They can drift relatively freely through the material, hopping from atom to atom, forming a kind of mobile sea of charge, threading through the fixed lattice of atomic nuclei. This is why metals conduct electricity and most other materials do not. Metals have these free electrons available to move. Now, when you connect a wire to a battery, you create something that pushes on those free electrons. The battery sets up a difference in electrical conditions between its two ends, a kind of pressure, often called voltage. That pressure acts through the electromagnetic field on the free electrons in the wire, nudging them all to drift in the same general direction. This collective drift of countless electrons through the wire is an electric current. And electric current is simply charge on the move. Everything electrical in your life is, at root, the controlled movement of charge. When you switch on a light, you are completing a path that lets electrons flow, and that flow heats a filament until it glows. When a motor spins, electric current flowing through coils creates magnetic effects that turn a shaft. When information travels through the wires of a computer, it moves as patterns of charge, surges and pauses that encode the ones and zeros of digital logic. Every device, every circuit, every spark of electrical technology that built the modern world is charge in motion, guided and channeled by human ingenuity. And here is the remarkable thing. The reason any of this is possible, the reason electrons respond to electrical pressure and flow obediently through wires, is, once again, that they carry charge. The electromagnetic field can push on them precisely because they are coupled to it. An uncharged particle could sit in a wire forever, and no voltage would ever budge it. It is the electron's charge, that same unexplained coupling, that allows it to be herded, directed, and put to work. The entire electrical age rests on this fact. There is a beautiful unity hiding here that took humanity a long time to uncover. For most of history, electricity and magnetism were thought to be separate phenomena. Electricity was the business of sparks and amber and lightning. Magnetism was the business of lodestones and compasses pointing north. They seemed unrelated. But over the course of the 1800s, scientists discovered that they are two faces of a single thing. A moving charge, an electric current, produces a magnetic effect around it, and a changing magnetic effect can push charges into motion, creating a current. Electricity and magnetism are not separate at all. They are deeply intertwined, two aspects of one underlying electromagnetic field. There is a way to see this unity that is stranger and more startling than simply saying the two are connected, and it reaches right down to the role of charge. It turns out that whether you see an electric force or a magnetic force can depend on how you are moving. The very same situation, involving the very same charges, can look purely electric to one observer and partly magnetic to another, simply because the two observers are moving differently. Electricity and magnetism are not just related. They are two views of one thing, seen from different states of motion. Consider a charge sitting still in front of you. Because it is at rest, it surrounds itself with a steady electromagnetic field, and another charge nearby feels an ordinary electric push or pull, attraction or repulsion, set in strength by the charges involved. There is no magnetism in this picture at all, because nothing is moving. It is a purely electric situation. But now imagine watching that same charge while you yourself drift past it. From your moving point of view, the charge is no longer at rest. It appears to be moving because you are moving relative to it. And a charge in motion, as we have seen, produces a magnetic effect. So from your perspective, there is now a magnetic field present that the stationary observer did not see at all. Same charge, same arrangement, but one observer reports a purely electric situation, while the other reports a mixture of electric and magnetic effects. Neither is wrong. The split between what we call electric and what we call magnetic is not absolute. It depends on the motion of whoever is looking. This is one of the deepest insights buried inside the unification of the two forces, and it tells us that magnetism is, in a real sense, what electric charge looks like when it is in motion relative to you. The two forces are not separate things that merely interact. They are a single electromagnetic interaction, and whether it shows its electric face or its magnetic face is partly a matter of your own frame of motion. And beneath both faces, generating both, sits the same fixed property, the charge of the particles involved. Charge is the common root from which both the electric and the magnetic spring, and the division between them, dissolves the moment you start to move. This unification was one of the great triumphs of physics, and it has a direct bearing on charge. It means that the magnetism you encounter in everyday life, the magnet holding a note to your refrigerator, the compass guiding a ship, the magnetic fields that store data and run motors, is ultimately connected to charge as well. The magnetism of an ordinary magnet arises from the behavior of charged electrons inside its atoms, from the way they move and align. Charge in motion is magnetism. The two phenomena that once seemed so different are bound together by the same field, and charge sits at the heart of both. Now we arrive at what may be the most astonishing consequence of charge of all, the one that, quite literally, lets you experience the universe. We have seen that a charge at rest sets up a field around it, and that a charge in steady motion creates a magnetic effect. But what happens when a charge accelerates, when it speeds up, slows down, or changes direction? When a charged particle accelerates, it does something extraordinary. It sends a ripple outward through the electromagnetic field. Picture dropping a stone into a still pond. The impact sends circular waves spreading across the surface in every direction, carrying energy away from the point where the stone struck. An accelerating charge does something similar to the electromagnetic field. The sudden disturbance it creates does not stay put. It propagates outward, a self-sustaining wave travelling through the field at enormous speed. And that wave, that ripple in the electromagnetic field, launched by an accelerating charge, is electromagnetic radiation. But why must the charge accelerate? Why does a charge sitting still, or even a charge gliding along at a steady speed, not throw off light, while a charge that speeds up or changes direction does? This is a subtle and beautiful point, and it sits right at the boundary between the quiet field and the travelling wave. Consider first a charge at rest. It fills the space around it with a steady, unchanging electromagnetic field, a fixed pattern of influence reaching out in every direction, the same from one moment to the next. Nothing about it changes, so nothing travels outward. The field is simply there, draped around the charge like a still, unmoving shape. No energy radiates away. The charge sits, and its field sits with it. Now set the charge moving at a perfectly steady pace, neither speeding up nor slowing down, nor turning. Its field travels along with it, carried smoothly through space, still a settled pattern that simply moves as a whole. There is no abrupt change, no disturbance that detaches itself and races away. A charge in steady, unchanging motion still does not radiate. Its field rides along with it, undisturbed. The crucial ingredient is change in the motion, acceleration. When a charge suddenly speeds up, slows down, or changes direction, its field cannot instantly rearrange itself everywhere at once. The field nearby adjusts quickly, but the field farther out has not yet received the news, because no influence can travel faster than the speed of light. The result is a kink, a sudden bend in the pattern of the field, a place where the field has to abruptly catch up to the charge's new motion. And that kink does not stay attached to the charge. It detaches and travels outward on its own, a self-sustaining ripple racing away at the speed of light, carrying energy with it. That detached, travelling kink is the electromagnetic wave. It is light. So the deep requirement for radiation is a change in motion. A charge must be shaken, pushed, jolted, turned, made to alter its course, for it to cast off waves. This is why the charges in an antenna are driven to surge back and forth, reversing direction over and over. Each reversal is an acceleration, and each acceleration launches another ripple into the field. It is why the charged particles churning in the chaos of the sun, constantly buffeted and redirected, pour out light without ceasing. Wherever you find light being born, you will find charges being accelerated, shaken hard enough to throw a piece of their field loose and send it travelling out into the universe. This is one of the deepest and most beautiful facts in all of physics. Accelerating charges radiate. They throw off waves of electromagnetic energy, and those waves are not some exotic, rare phenomenon. They are, depending on their wavelength, the radio waves that carry music to your car, the microwaves that heat your food, the infrared warmth you feel from a fire, the visible light that fills your days, the ultraviolet rays that tan and burn your skin, the X-rays that reveal your bones, and the gamma rays born in the violence of stars and atomic nuclei. All of these are the same kind of thing, electromagnetic waves, differing only in their wavelength. And every one of them is created somewhere by charges in accelerated motion. Let that sink in fully. The light entering your eyes at this very moment was produced by accelerating charges. In the screen you may be looking at, electrons are being driven to jostle and shift, and as they do, they cast off light. In the sun, 93 million miles away, charged particles in a churning, blazing plasma are accelerating constantly, flooding the solar system with light that took 8 minutes to reach you. In every lamp, every flame, every glowing thing, the story is the same. Charges, accelerating, shaking the electromagnetic field into waves that travel outward and eventually strike the back of your eye, where they are absorbed and turned into the signals your brain reads as vision. And the absorption is just as much a charge phenomenon as the emission. When light reaches your eye, it is detected because the electromagnetic wave pushes on charged particles in the cells of your retina. The wave, being a disturbance in the electromagnetic field, can grip anything that is coupled to that field, anything that carries charge. The molecules in your retina respond, change shape, and trigger the cascade of signals that becomes sight. So both ends of the act of seeing, the creation of light and its detection, are charge at work. Without charge, there would be no light to emit and nothing to receive it. The universe would be not merely dark, but fundamentally blind, a place where the electromagnetic field could carry no messages because nothing was connected to it. Think about how much of our knowledge of the universe comes to us as light. Nearly everything we know about the distant cosmos, the composition of stars, the motions of galaxies, the existence of planets around other suns, the echoes of the universe's birth, reaches us as electromagnetic radiation collected by our eyes and our telescopes. And all of it was launched on its journey by accelerating charges somewhere long ago. The light from a star that left before you were born, crossing the void to reach you tonight, began as charged particles accelerating in that star's furnace. Charge is not just the architect of matter, it is the universe's voice, the means by which one part of the cosmos can signal another across unimaginable distances. Now let us draw all of these threads together, because the pattern they form is the real point. We began with one fixed, unexplained property, the electron's coupling to the electromagnetic field, identical for every electron in existence. And from that single property, watch what unfolded. Like charges repel and opposite charges attract, and from that, atoms form, as electrons are bound to nuclei. From atoms come the elements, the entire periodic table. From the interactions of atoms comes chemistry, and from chemistry comes the staggering complexity of life. Charge in motion gives us electricity, the lifeblood of modern civilization. Charge in motion is also magnetism, the partner of electricity in the unified electromagnetic field. And accelerating charge gives us electromagnetic radiation, radio, light, X-rays, the whole spectrum, including the very light by which you perceive the world. Almost everything you have ever experienced traces back, through one chain of reasoning or another, to electric charge. The solidity of the ground beneath you is electromagnetic, atoms refusing to pass through one another because their electrons repel. The warmth of sunlight is electromagnetic. The colors you see, the sounds you hear translated through electronic devices, the food you eat and the way your body digests it, the thoughts in your brain carried by signals that are partly electrical, the screen in front of you and the device behind it, all of it is charge, doing what charge does, governed by that single fixed coupling to the field. This is what makes the mystery from before so striking. We are not talking about some obscure, marginal quantity that matters only in specialized experiments. We are talking about the property that underwrites the everyday world in its entirety. The number we cannot explain is the number that makes the universe the kind of place that can contain atoms, chemistry, light, and life. It is hard to imagine a more consequential piece of unexplained physics. The dial we cannot account for is the dial on which existence itself, as we know it, depends. And there is a unity in all of this that deserves to be appreciated for its own sake. It would have been reasonable, before we knew better, to imagine that the forces holding atoms together, the forces driving electricity, the phenomenon of magnetism, and the nature of light were all separate mysteries requiring separate explanations. But they are not. They are all the same phenomenon, seen from different angles. They are all the electromagnetic interaction, charge talking to the field, and the field talking back. Binding, repelling, flowing, radiating. These are not four different things. They are four different expressions of one thing. And that one thing has, at its core, the electron's charge. There is a temptation, having seen all this, to feel that we must therefore understand charge deeply. After all, we can predict every one of these behaviors. We can calculate the forces between charges, design circuits down to the finest detail, engineer lasers and antennas and computer chips, and forecast the behavior of light to extraordinary precision. Surely a property we can wield so masterfully must be a property we comprehend at its foundation. But this is exactly the trap we must avoid. There is a vast difference between knowing what charge does and knowing what charge is or where it comes from. We have spent this whole stretch of our journey cataloguing what charge does, and it does a great deal, more than almost anything else in physics. Yet not one of these triumphs touches the underlying question. We can describe, predict, and harness the consequences of the electron's charge with overwhelming success, while remaining entirely in the dark about why the electron has that charge at all. Mastery of the consequences is not the same as understanding the cause. A skilled sailor can read the wind and ride it perfectly without knowing the deep physics of why air moves. We are, in a sense, master sailors of the electromagnetic sea, and we still cannot say why the wind blows. This distinction is going to grow more important as we continue, because the deeper we look, the clearer it becomes that our extraordinary ability to work with charge has, in a way, disguised our ignorance of it. The successes are so complete, so practical, so woven into our technology and our understanding, that it is easy to assume the foundational questions must have been answered along the way. They have not. They have simply been set aside, quietly assumed, while the magnificent superstructure of electromagnetic science was built on top of them. So let us hold on to the picture we have assembled. One fixed, universal, intrinsic property of the electron, its coupling to the electromagnetic field, reaches outward and builds the world. It binds electrons to nuclei, assembling atoms. It governs how atoms join, creating chemistry and life. It flows through wires as electricity and reveals itself as magnetism. It radiates as light, letting the universe be seen and letting us see it. From a single number, an entire reality unfolds. And yet that number remains a stranger to us. We have followed it out into the world and watched it perform miracle after miracle. We have not, in all this watching, come one step closer to knowing where it came from. The more we see charge accomplish, the more pressing the original question becomes. A property this powerful, this universal, this fundamental to everything, surely it must come from somewhere, must mean something, must rest on some deeper foundation. That is the question we turn to next. Having seen what charge does, we will now press inward and ask what charge is made of. Whether the electron hides smaller pieces within it, why charge always seems to come in identical, indivisible packets, and what it means that two utterly different particles, the electron and the proton, can carry charges so perfectly matched in size. The behaviors we have explored are the surface. Beneath them lies a structure stranger and more puzzling than the everyday world ever lets on. We have watched charge build the world. Now we turn the question inward and ask what charge itself is built from. It is the most natural question imaginable, the same question that has driven physics for centuries. Whenever we have found something we did not understand, our instinct has been to look inside it, to take it apart, to find the smaller pieces that make it up, and explain the whole in terms of its components. We did this with matter and found atoms. We did it with atoms and found a nucleus surrounded by electrons. We did it with the nucleus and found protons and neutrons. We did it with protons and neutrons and found quarks. Each time the strategy worked. Each time the mystery dissolved into smaller, simpler parts. So let us apply the same strategy to charge. The electron carries a charge. What is that charge made of? What are the smaller pieces inside the electron that generate it? If we could just crack the electron open and peer inside, surely we would find the machinery that produces its charge, just as cracking open the atom revealed the particles within. But here, the strategy that has served us so faithfully for so long runs into a wall. Because when we look as hard as we possibly can at the electron, and we have looked extraordinarily hard, we find nothing inside it. No smaller pieces, no internal parts, no machinery. The electron appears to be, as far as every experiment has ever been able to determine, a true point. A particle with no size, no internal structure, and no smaller charged components hidden within. This is one of the strangest facts in all of physics, and it deserves to be examined carefully, because it overturns the entire approach we have relied on. Let me explain how we know it and what it means. To probe the inside of something, you have to hit it with something else and watch how it bounces. This is exactly what physicists did to discover the structure of the atom. They fired small, fast particles at atoms and watched how they scattered. The way the particles bounced revealed that the atom had a tiny, dense core, the nucleus, surrounded by mostly empty space. The pattern of the bouncing was the fingerprint of the internal structure. If a thing has parts inside it, those parts affect how other particles scatter off it, and from the scattering pattern you can reconstruct what is in there. So physicists have done the same thing to the electron with the most powerful tools available. In enormous machines called particle accelerators, electrons are smashed together and probed at staggeringly high energies, which is equivalent to examining them at incredibly small scales. The higher the energy, the finer the detail you can resolve, the deeper you can see. And across decades of these experiments, the result has always been the same. The electron shows no sign of internal structure. It behaves exactly as a point would behave. No matter how hard we hit it, no matter how finely we look, no smaller pieces appear. There is no scattering pattern that betrays hidden parts, because as far as we can tell, there are no hidden parts. We can even put a number on how small the electron must be. The experiments tell us that if the electron has any size at all, it must be smaller than a certain limit, and that limit is extraordinarily tiny, vastly smaller than a proton, smaller than anything we have ever found structure in. For all practical and theoretical purposes, the electron is treated as a genuine point particle, an object of zero size. It is not a tiny ball. It is not a little sphere of charge. It is a point, and a point has no inside. Now consider what this does to our question. We wanted to explain the electron's charge by finding the smaller charged pieces within it, but there are no smaller pieces. The charge is not assembled from anything. It is not the sum of tinier charges arranged inside a structure. It is not produced by internal currents or spinning components or any hidden mechanism, because there is no hidden interior for such a mechanism to occupy. The charge simply belongs to the point, intrinsically, as a bare feature of what the electron is. This is a genuine dead end for the take-it-apart strategy, and it is worth pausing to feel the weight of that. For the entire history of physics, the answer to where does this property come from has been look at the smaller parts. With the electron's charge, that answer is unavailable. There are no smaller parts. We have hit the bottom of that particular ladder. The charge is fundamental in the most literal sense. It is not built up from anything more basic. It is a starting ingredient of reality, not a result of deeper structure. You might wonder whether this is just a temporary limitation, whether better machines, higher energies, finer probes might eventually reveal structure inside the electron that we simply cannot see yet. It is a fair thought, and we should be honest that we can never prove, with absolute certainty, that the electron has no structure at all. We can only say that down to the smallest scales we have ever been able to examine, none has appeared. But the point particle picture is not merely a confession of ignorance. It is woven deeply into our most successful theories, which treat the electron as a point, and in doing so, make predictions of breathtaking accuracy. Predictions that match experiment to many decimal places. If the electron secretly had structure, that structure would, in general, leave traces in these ultra-precise measurements. So far, it has left none. The point particle is not a placeholder we are waiting to replace. It is, as far as all the evidence goes, the real picture. Before we move on, this picture of the electron as a perfect point carries a hidden difficulty that is worth confronting directly, because it is one of the most honest cracks in our understanding of charge, and almost nobody outside physics has heard of it. It is sometimes called the self-energy problem, and it arises the moment you take seriously the idea of a charge concentrated at a single point with no size at all. Recall that a charge fills the space around it with an electromagnetic field, and that this field contains energy. The closer you get to the charge, the stronger the field becomes. Now ask what happens if the charge truly sits at a single point of zero size. As you imagine approaching that point, the field grows stronger and stronger without limit, climbing toward infinity as the distance shrinks toward nothing. And when you add up all the energy stored in that ever-strengthening field, packed into the space immediately around the point, the total comes out infinite. A genuine point charge, taken literally, would carry an infinite energy in its own surrounding field. This is plainly a problem. The electron does not have infinite energy. It has a perfectly ordinary, finite, well-measured mass and energy. So something is wrong with the naive picture of a bare point charge sitting alone with its field. The mathematics, pushed to its literal conclusion, produces an infinity that the real electron simply does not have. This is not a small technical wrinkle. It is a sign that our most straightforward way of imagining a charged point particle breaks down at the very smallest scales, exactly where we would most want it to work. Physicists have learned to handle these infinities with a set of careful mathematical techniques that, in effect, tame the problematic quantities and allow the theory to produce its famously accurate predictions anyway. These techniques work, spectacularly well in fact. But many of the physicists who developed and used them have been candid that they feel more like a clever way of stepping around the infinity than a true resolution of it. The infinity is managed, not understood. And it is a reminder that beneath the smooth, successful surface of our theory of charge lies a foundation that, when examined too closely, refuses to behave. The point charge that our experiments seem to reveal is, in the raw mathematics, an object that should carry an impossible, infinite energy. And squaring that circle remains part of the unfinished business at the heart of what charge is. So we are left with charge as an irreducible property of a structureless point. And this leads us to an even deeper puzzle, one that the everyday world hides from us completely. Charge does not come in just any amount. It comes in packets. It is quantized. Let me explain what this means, because it is one of the most profound and least appreciated facts about charge. In our everyday experience, most quantities seem to be smooth and continuous. You can have any amount of water you like, a litre, half a litre, a third of a litre, any fraction at all, down as fine as you please. You can pour off a little more, a little less, in a continuous flow. There is no smallest possible drop of water below which you cannot go. Length seems continuous too, and so does time and weight. The world of ordinary experience feels smooth, infinitely divisible, with no fundamental graininess. But charge is not like that. Charge comes in discrete, indivisible units. There is a smallest possible amount of charge, the amount carried by a single electron, and every charge you will ever find in nature is a whole number multiple of that basic unit. You can have the charge of 1 electron, or 2 electrons, or 1,000, or 1 billion. But you can never have 1.5 electrons worth of charge. You cannot have 1/3 of it, or 1/10, or any fraction at all. Charge is granular. It comes in lumps. The basic lump is the charge of the electron, and nature deals only in whole numbers of these lumps. This is genuinely astonishing when you sit with it. Imagine if water behaved this way. If there were a smallest possible amount of water, a single fundamental droplet, and you could only ever have whole numbers of these droplets, never a fraction of one. That is exactly how charge behaves. There is a fundamental quantum of charge, and all charge in the universe is built from whole number multiples of it. Why is charge quantized? Why does it come in identical, indivisible packets rather than as a smooth, continuous quantity that could take any value? This too is a question that our current physics describes far better than it explains. We know with overwhelming experimental certainty that charge is quantized. We have measured the charges of countless particles, and they always come out as whole number multiples of the fundamental unit. The quantization is one of the most solidly established facts in physics. But the deep reason for it, why the universe insists on dealing in identical charge packets rather than a continuous smear, remains, at the foundational level, unexplained. There is, however, one genuinely remarkable idea about why charge might be quantized, an idea so elegant that physicists have found it hard to dismiss, even though it rests on something that has never been seen. To understand it, we have to return for a moment to magnetism, and to a curious asymmetry hiding inside the relationship between electricity and magnetism. Electric charge comes in two kinds, positive and negative, and crucially, you can have one without the other. You can isolate a single positive charge all by itself. You can isolate a single negative charge. They exist independently. But magnetism behaves differently. Magnets always come with two poles, a north and a south, bound together. Cut a magnet in half, hoping to separate the north pole from the south pole, and you do not get an isolated north and an isolated south. You get two smaller magnets, each with its own north and south. No matter how finely you divide it, every piece has both poles. In all of nature, as far as anyone has ever found, an isolated single magnetic pole simply does not exist. But suppose, just suppose, that somewhere in the universe even one such object did exist. A lone magnetic pole, a north without a south, what physicists call a magnetic monopole. Here is the astonishing thing. A profound piece of mathematics shows that if even a single magnetic monopole exists anywhere in the entire universe, then electric charge everywhere must be quantized. The mere existence of one isolated magnetic pole, somewhere, anywhere, would force every electric charge in the cosmos to come in discrete, identical packets, exactly the quantization we observe. The two facts would be locked together. One lonely monopole would explain, in a single stroke, why the electron's charge comes in indivisible units and why every charge in nature is a whole number multiple of the same fundamental amount. This is a breathtaking possibility, because it would turn the deep mystery of quantization into a consequence of something else. Instead of charge simply happening to come in packets for no known reason, it would come in packets because somewhere, perhaps, a magnetic monopole exists and demands it. The strangeness of quantization would be traded for the strangeness of the monopole, but at least the two would be connected, and the quantization would have a reason behind it. And yet, and this is the heart of it, no magnetic monopole has ever been found. Physicists have searched for them in many ways, in cosmic rays, in matter, in the debris of high-energy collisions, in ancient rocks. None has ever turned up. So we are left with an idea of great beauty that would explain why charge is quantized, attached to an object that may not exist. The quantization is real and certain. The explanation that would account for it hangs on a hypothetical particle nobody has ever detected. It is, once again, the same pattern that haunts this entire subject. We can describe the quantization of charge with total confidence, and the one elegant idea that might explain it remains unconfirmed, waiting on a discovery that has never come. The deepest available answer to why charge comes in packets is itself a question mark, and quantization is intimately connected to that uncanny universality we keep returning to. Because charge comes in identical packets, every electron carries exactly the same charge. There is no room for variation. An electron cannot carry slightly more than one unit or slightly less, because charge does not come in slightly more or slightly less amounts. It comes in whole units, and the electron carries exactly one of them, negative. This is part of why every electron is a perfect clone of every other in this respect. The quantization enforces the sameness. The packets are identical because they are the same fundamental unit repeated. Now I have to add a wrinkle, because the full story of charge quantization is richer and stranger than what I have said so far. When physicists looked inside the proton, which, unlike the electron, does have internal structure, they found the quarks we mentioned earlier. And the quarks turned out to carry charges that are fractions of the electron's charge. Some quarks carry 2/3 of a unit of positive charge. Others carry 1/3 of a unit of negative charge. This might seem to violate everything I just said about charge coming in whole units. How can there be particles with fractional charge if charge is quantized in whole units of the electron's charge? The resolution is beautiful and deepens the mystery rather than resolving it. Quarks are never found alone. They are always bound together in combinations, locked inside particles like the proton and neutron, and they combine in precisely such a way that their fractional charges always add up to whole number multiples of the electron's charge. A proton, for instance, is made of 3 quarks, whose fractional charges sum to exactly 1 full unit of positive charge, exactly the opposite of the electron's charge. The fractions, when combined, always produce whole units. You can never isolate a quark to see its fractional charge on its own. Nature keeps them bundled so that what emerges into the world is always a whole number of fundamental units. So even with quarks in the picture, the charges of all freely existing particles remain whole number multiples of the electron's charge. The quantization holds at the level of everything we can actually isolate. This brings us to perhaps the most haunting fact in this entire subject. A coincidence so precise, so perfect, and so utterly unexplained that physicists have puzzled over it for a very long time. It is the matching of the electron's charge and the proton's charge. The electron and the proton could hardly be more different. The proton is nearly 2,000 times heavier than the electron. The proton has internal structure. It is built from quarks, bound together by their own forces. The electron, as we have seen, is a structureless point with no parts at all. They are produced by entirely different processes. They participate in different combinations of forces. By almost every measure, the electron and the proton are profoundly dissimilar objects. They are not 2 versions of the same thing. They are deeply, fundamentally distinct. And yet, their charges are exactly equal in size and exactly opposite in sign. The proton carries a positive charge precisely equal in magnitude to the negative charge of the electron. Not approximately equal, not roughly the same. Equal to a degree of precision that staggers the imagination. Experiments comparing the 2 charges have found them identical to many decimal places, with no detectable difference whatsoever. If there were even the tiniest mismatch between the size of the proton's charge and the size of the electron's charge, it would show up in the behavior of ordinary matter, because ordinary atoms contain equal numbers of protons and electrons and are observed to be electrically neutral to extraordinary precision. The exquisite neutrality of bulk matter tells us that the charges balance with breathtaking exactness. It is worth understanding how we actually know the matching is so precise, because the method is itself a beautiful piece of reasoning, and it shows that this is no vague impression, but a hard, tested fact. The argument runs through the electrical neutrality of ordinary matter. Consider any ordinary lump of material, a gas, a liquid, a solid, anything made of ordinary atoms. Each atom contains a certain number of protons in its nucleus and an equal number of electrons around it. If the proton's charge and the electron's charge were exactly equal and opposite, then each atom would be perfectly neutral, its positive and negative charges cancelling without remainder, and the whole lump of material would carry no net charge at all. But suppose there were the tiniest mismatch. Suppose the proton's charge were just slightly larger in size than the electrons by some minuscule amount. Then each atom would carry a tiny leftover charge, a faint imbalance. And in a lump of material containing an astronomical number of atoms, all those tiny leftover charges would add up. The material as a whole would carry a measurable net charge, and lumps of material would push or pull on one another with an electrical force. So physicists devised exquisitely sensitive experiments to look for exactly this. They took quantities of gas and other materials containing enormous numbers of atoms and searched for any net charge, any faint electrical force, any sign that the protons and electrons did not quite cancel. And they found nothing. The materials came out neutral to an astonishing degree. The absence of any detectable net charge, even across vast numbers of atoms, where the tiniest per-atom mismatch would have accumulated into something visible, places an extraordinarily tight limit on how different the two charges could possibly be. The conclusion is that the proton's charge and the electron's charge match in size to many decimal places, a precision wrung not from measuring the two charges separately and comparing them, but from the sheer, stubborn neutrality of the everyday matter all around us. The world's refusal to carry a net charge is the evidence, and it is evidence of remarkable power. Now ask yourself why this should be so. The electron and the proton are completely different particles, made differently, behaving differently, with nothing obvious in common. Why should their charges match so perfectly? It is as though you discovered that the weight of a feather and the weight of an entirely unrelated grain of dust, chosen for no particular reason, were identical to 40 decimal places, and not just for one feather and one grain, but for every feather and every grain, everywhere, always. You would be certain that some deep principle was at work, some hidden law enforcing the match. And yet, in the case of the electron and the proton, our current understanding offers no confirmed reason for the perfect equality. It is observed, it is established beyond doubt, but it is not, at the deepest level, explained. This matching is not a minor curiosity. It is one of the great unsolved riddles tucked inside the foundations of physics. The fact that the charge of a simple point particle and the charge of a complicated composite particle, built from fractionally charged quarks no less, come out exactly equal and opposite seems to demand an explanation. Surely it cannot be mere coincidence. Surely there must be some reason the universe arranges its charges so that the negative of the electron precisely cancels the positive of the proton, allowing atoms to be neutral and matter to be stable. But the reason, if there is one, has not been confirmed. We can state the fact with total confidence. We cannot say why it is true. Physicists have ideas about where such an explanation might come from, frameworks that attempt to relate the electron and the proton's constituents within larger, more unified structures, in which the charge matching would emerge as a necessary consequence rather than an accident. These are serious, sophisticated efforts, but they remain unconfirmed. No experiment has yet verified them. They are possibilities, not established truths. And so the matching of the electron and proton charges stands, for now, as one more precisely known yet unexplained fact in a subject that is full of them. Step back and survey what we have found by looking inward. We set out to explain the electron's charge by finding what it is made of, and at every turn, the search for deeper structure has come up empty in exactly the way that deepens the mystery rather than resolving it. The electron has no internal parts. Its charge is not built from smaller charges. Charge comes in identical, indivisible packets, and we cannot explain why it is quantized rather than continuous. Every electron carries exactly the same packet with no variation, and we cannot explain the source of that perfect uniformity. And the electron's charge matches the proton's charge to staggering precision, despite the two particles being utterly different, and we cannot explain the match. Notice the pattern in all of this. Each time we press the question deeper, we find not an explanation, but another precisely characterized fact that itself cries out for explanation. The charge is intrinsic. Fact, not explanation. The charge is quantized. Fact, not explanation. The charge is universal. Fact, not explanation. The charge matches the protons. Fact, not explanation. We keep arriving at bedrock, at properties that simply are the way they are, with no deeper layer beneath them that we have been able to uncover. The take-it-apart strategy, which has been the great engine of physics for centuries, has carried us all the way down to the electron and then stopped, because there is nothing smaller to take apart. This is humbling, and it is important to be clear-eyed about it. It would be easy to gloss over these gaps, to let the precision of our measurements and the success of our theories create the impression that the foundational questions are answered. They are not. The electron's charge is, in a real sense, a brute fact of our universe, a property that our best physics takes as a given, characterizes with extraordinary precision, and uses to predict an enormous range of phenomena, without being able to say where it comes from or why it has the form it has. And yet, there is something to add here that keeps this from being a story of pure failure. The very fact that we can state these mysteries so precisely is itself a remarkable achievement. We know that the electron is a point to within astonishing limits. We know that charge is quantized to overwhelming certainty. We know that the electron and proton charges match to many decimal places. These are not vague impressions. They are hard, quantitative facts, established by some of the most careful experiments ever performed. We have mapped the boundary of our ignorance with extraordinary precision. We know exactly what we do not know. And in science, knowing precisely where the mystery lies is the first and most essential step toward, one day, perhaps, solving it. There is also a question lurking here that we have not yet fully confronted, and it points the way forward. We have said repeatedly that our theories describe charge superbly while failing to explain it. But what exactly do those theories say? How does our best account of charge, the framework physicists actually use, the one that delivers those 11 decimal place predictions, handle this property whose origin is so mysterious? If charge is not made of smaller pieces, and if the theory does not explain where its value comes from, then what does the theory do with charge? How does it incorporate something so fundamental and so unexplained, and still produce predictions of such overwhelming accuracy? That is the question we turn to next. We will look closely at how modern physics actually treats charge, how it builds charge into its equations as a fundamental coupling, how a deep and elegant principle called symmetry organizes the electromagnetic interactions into their beautiful and successful form, and how a single famous number captures the overall strength of the electron's grip on the field. And then we will draw the most important distinction of this entire journey: the line between describing charge, which our theories do with unmatched success, and explaining charge, which they do not do at all. For it is one thing to write down with perfect precision how charge behaves. It is another thing entirely to say why charge exists, and why it takes the exact form it does. The first, physics has mastered. The second remains open. One of the most precisely measured, yet most deeply unexplained features of the world. We have arrived at the most important distinction of this entire journey, and it is one that the very success of physics tends to hide. So let me state it plainly before we go any further. There is a profound difference between describing something and explaining it. To describe charge is to write down with precision how it behaves, what it does, how strongly it acts, what consequences follow from it. To explain charge is to say why it exists at all, why it has the value it has, where it ultimately comes from. Modern physics describes charge with an accuracy that is among the greatest achievements in the history of human thought. And modern physics does not explain charge at all. Holding both of those truths at once is the key to understanding where we really stand. To see this clearly, we need to look at how our best theory of charge actually works. That theory has a name: quantum electrodynamics. It is the theory of how charged particles and light interact, how electrons and the electromagnetic field talk to each other in the full language of quantum mechanics. And it is, by a wide margin, the most precisely tested theory in all of science. Its predictions have been checked against experiment again and again, and they agree to a staggering number of decimal places. There are quantities that quantum electrodynamics predicts and that experiments measure, and the two match to something like 11 or 12 significant figures. To grasp how extraordinary that is, imagine measuring the distance from one coast of a continent to the other, and having your prediction come out correct to within the width of a single human hair. That is the kind of agreement we are talking about. It is almost unimaginable precision, and it is routine in this field. So here we have a theory of charge that works better than almost anything else humans have ever devised. Surely, you might think, such a theory must explain charge. How could it be so accurate otherwise? But here is the crucial point, and it is the heart of everything. Quantum electrodynamics achieves all of its astonishing precision while taking the electron's charge as an input, not as something it explains. Let me make this concrete. In the equations of quantum electrodynamics, the strength of the electron's coupling to the electromagnetic field appears as a number that physicists refer to as the coupling constant. This number measures how strongly the electron interacts with the field, which is precisely what charge controls. And where does the value of this number come from within the theory? It does not come from anywhere within the theory. It is measured in the laboratory and then inserted into the equations by hand. The theory does not derive it. The theory does not predict it. The theory cannot tell you why it has the value it has, rather than some other value. The theory simply takes the measured value as a given and proceeds from there. There is a further twist here that makes the situation stranger still, and it overturns one of the assumptions we have been quietly carrying. We have been speaking of the electron's charge as a single, fixed number, the strength of its coupling to the field. But that strength, it turns out, is not quite as fixed as it appears. The measured value depends on how closely you look. This sounds almost paradoxical, so let me explain what is meant. When physicists probe the electron at low energies, examining it gently from a relative distance, they measure a certain strength for its electromagnetic coupling. But when they probe it at very high energies, smashing particles together violently so as to examine the electron at extremely small scales, they find that the effective strength of the coupling is slightly larger. The closer in you look, the more strongly the electron seems to couple to the field. The interaction strength is not one single number etched permanently into the electron. It changes gradually, depending on the scale at which it is measured. Physicists call this the running of the coupling. Why does this happen? The answer lies in the restless nature of empty space itself. In the modern picture, the vacuum around an electron is not truly empty. It seethes with fleeting activity, pairs of particles flickering briefly into existence and vanishing again, too quickly to be caught directly, but real enough to leave their mark. These flickering pairs arrange themselves around the electron and partially screen its charge, like a faint haze surrounding it that softens its influence when viewed from afar. When you look at the electron from a distance, you see it through this haze, and the charge appears somewhat weaker. When you push in close, penetrating the haze, you see more of the electron's bare influence, and the coupling appears stronger. The screening thins as you approach, and so the measured strength climbs. This is a genuine, measured effect, confirmed in experiments, and it is described with great precision by the theory. But notice what it does to our question. It means that even the value we plug into our equations is not a simple, absolute, once-and-for-all constant. It is a quantity that shifts with the scale of observation, shaped by the activity of the vacuum itself. And the theory describes how it shifts with beautiful accuracy. Yet it still does not tell us where the underlying coupling comes from, or why it has the particular value it has at any given scale. The running of the coupling is one more thing our theory describes superbly and explains not at all. The charge is not even a fixed dial. It is a dial whose reading depends on how hard you stare at it, and we can predict exactly how the reading changes, while remaining completely in the dark about why the dial exists or what set its underlying position in the first place. This is the pattern we identified at the very beginning, now seen in full and precise detail. The Standard Model and quantum electrodynamics within it assumes the electron's charge rather than explaining it. The charge is one of those free parameters, those dials of the universe, that must be measured rather than calculated. Quantum electrodynamics is, in essence, a magnificent machine for taking the measured value of the charge and using it to predict with overwhelming accuracy what charged particles will do in every conceivable situation. Feed in the charge, and the theory will tell you, to 11 decimal places, how an electron behaves in a magnetic field, how light scatters off matter, how atoms emit and absorb radiation, how charged particles deflect one another. But the theory will never tell you why the number you fed in has the value it does. That value is its starting point, not its conclusion. I want to dwell on this because it is so easy to miss and so important. The precision of quantum electrodynamics can create a powerful illusion. When a theory predicts something to 11 decimal places, our instinct is to feel that the theory must understand that thing completely, down to its foundations. But precision of description is not the same as depth of explanation. Quantum electrodynamics describes the consequences of charge with perfect precision. It says nothing about the origin of charge. A perfect map of where a river flows is not the same as an account of why the river exists. We have a perfect map. We do not have the deeper account. Now, there is a beautiful and important piece of structure inside the theory that we need to understand, because it is sometimes mistaken for an explanation of charge when it is something subtler. This is the principle of gauge symmetry. It is one of the deepest ideas in modern physics, and it lies at the very heart of how electromagnetism is built into our theories. But understanding what it does, and what it does not do, is essential to seeing the true shape of the mystery. Let me try to convey what gauge symmetry is in plain terms. A symmetry, in physics, is a change you can make to a system that leaves something important unchanged. If you rotate a perfect sphere, it looks exactly the same afterward. That is a symmetry of the sphere. Physicists have discovered that the fundamental laws of nature possess various symmetries of this kind, certain changes you can make that leave the laws looking exactly the same. Gauge symmetry is a particular, rather abstract symmetry of this sort. It concerns a kind of freedom in how we describe the electromagnetic field and the charged particles within it. A freedom to make certain coordinated changes that remarkably leave all the physics unchanged. Here is the astonishing thing about gauge symmetry. If you start by insisting that the laws of physics must possess this particular symmetry, then the entire structure of electromagnetism follows almost as a consequence. The existence of the electromagnetic field, the way charged particles couple to it, the form of the forces between charges, Much of this can be seen as flowing from the requirement of gauge symmetry. It is a powerful and elegant organizing principle. It tells you the shape that electromagnetic interactions must take. It explains why the electromagnetic field exists in the form it does, and why charged particles interact with it in the particular pattern they do. For this reason, gauge symmetry is rightly celebrated as one of the great unifying insights of physics, and it extends far beyond electromagnetism to the other fundamental forces as well. So you might think that gauge symmetry is the explanation of charge we have been seeking. It organizes electromagnetism. It dictates the form of the interactions. Does it not, then, tell us where charge comes from? Here is the careful answer, and it is the crux of this whole stretch of our journey. Gauge symmetry organizes the electromagnetic interactions, but it does not, by itself, provide a simple mechanical source from which the electron receives its charge. It tells you the structure that charged interactions must have. It does not tell you why the electron carries the specific charge it carries, or why charge takes the discrete, quantized values it does, or where the particular strength of the coupling comes from. The symmetry shapes the framework within which charge operates. It does not hand you the charge itself with its precise value as a finished product. Think of it this way. Imagine you are told that a certain building must be perfectly symmetrical, that whatever is on the left side must mirror what is on the right. This is a powerful constraint. It tells you a great deal about the building's form. It rules out countless asymmetric designs. It organizes the architecture, but it does not, by itself, tell you how tall the building is, or what it is made of, or why it was built to that particular height. The symmetry constrains the form without fully determining every feature. Gauge symmetry plays a somewhat analogous role for electromagnetism. It is a profound constraint on the form that charged interactions take, but it is not a mechanism that manufactures the electron's charge and stamps it with a specific value. This is a subtle point, and it is often blurred in casual accounts, so let me be as clear as I can. Gauge symmetry is genuinely deep and genuinely explanatory in certain respects. It explains why electromagnetism has the structure it has. It is one of the most beautiful and successful ideas in all of physics. But it is not a complete answer to the question we have been asking, the question of where the electron's charge ultimately comes from and why it has its exact value. The symmetry provides the stage and the script for how charged particles must interact. It does not explain why the lead actor, the electron, carries precisely the charge it does. That value still has to be put in by hand, measured and inserted just as before. The symmetry organizes, it does not originate. There is a related number that captures the overall strength of the electromagnetic interaction, and it deserves a mention because it is one of the most famous and most pondered numbers in all of physics. It is called the fine structure constant. It is a pure number, a number with no units attached, the same in any system of measurement, that encapsulates how strongly charged particles interact electromagnetically. It combines the electron's charge with a couple of other fundamental constants of nature into a single dimensionless measure of electromagnetic strength. Its value is close to a particular small fraction, roughly 1 part in 137. The fine structure constant has fascinated physicists for generations, precisely because it is a pure number that seems to characterize the strength of electromagnetism in an absolute way. And like the electron's charge from which it is partly built, its value is measured, not explained. Nobody has derived from deeper principles why the fine structure constant has the value it does rather than some other value. It is another of the universe's unexplained constants, perhaps the most famous of them all. Great physicists have stared at that number and wondered what, if anything, determines it. No confirmed answer has emerged. It sits there, precisely measured, governing the strength of every electromagnetic interaction in the cosmos, as mysterious in its origin as the charge it helps to express. So now we can assemble the full and honest picture of where our understanding stands. We have a theory, quantum electrodynamics, that describes the behavior of charged particles with unrivaled precision. We have a deep organizing principle, gauge symmetry, that explains the structure of electromagnetic interactions. We have a famous pure number, the fine structure constant, that captures the overall strength of the electromagnetic force. These are towering achievements. Together, they represent one of the high points of human understanding of nature. And not one of them explains where the electron's charge comes from or why it has its exact value. This is the essential truth, and I want to make sure it lands with full force, because it is so easily obscured by the sheer brilliance of what we have accomplished. We can describe charge with overwhelming success and explain its origin not at all. The two facts coexist. They are not in tension. A theory can be perfectly accurate in its predictions while remaining silent about the deepest why. Quantum electrodynamics is exactly such a theory. It is a flawless description built upon an unexplained foundation. The foundation, the electron's charge with its precise universal quantized value, is taken as given, and everything magnificent is built on top of it, without that foundation itself ever being accounted for. It is worth being clear about what would count as a genuine explanation, so that we understand exactly what is missing. A real explanation of the electron's charge would do something the current theory does not do. It would derive the value of the charge from deeper principles, so that you could calculate it rather than having to measure it. It would tell you why charge is quantized, why it comes in identical, indivisible packets, as a necessary consequence of some more fundamental structure. It would explain why every electron carries exactly the same charge, and why the electron's charge matches the proton's so perfectly as inevitable results rather than as observed facts that happen to be true. A theory that did all of this would have explained charge. We do not have one. Now, I do not want to leave the impression that physicists have simply given up, or that no one has ever tried to push past this boundary. There have been, and continue to be, serious attempts to find a deeper theory in which the electron's charge and the other unexplained constants of nature would emerge as necessary consequences rather than as free inputs. Some of these efforts try to unify the different forces of nature into a single larger framework, within which the matching of the electron and proton charges, for instance, might appear as an inevitable result. Others explore the possibility that the particles we think of as fundamental points might, at some far deeper level, have a richer underlying nature that could give rise to their charges. These are ambitious, sophisticated, and in many cases mathematically beautiful ideas. But we must be honest about their status, in keeping with everything we have said. None of these deeper proposals has been confirmed by experiment. They remain possibilities, frameworks that might, one day, turn out to describe reality, or might not. They are not established knowledge. They have not solved the problem. The plain situation, as of now, is that the origin of the electron's charge is not understood. We do not have a confirmed mechanism that explains why the electron possesses its exact charge. To claim otherwise would be to overstate what physics has actually achieved, and the whole point of this journey has been to see clearly, without illusion, exactly what we know and exactly what we do not. And there is something genuinely valuable in seeing it clearly. It is tempting, in popular accounts of science, to present everything as solved, every mystery as conquered, every question as answered. But that picture is false, and it does a disservice to the real character of science. Science is not a finished edifice. It is a living enterprise, full of open questions, unexplained facts, and genuine mysteries sitting right at the foundations of even our most successful theories. The electron's charge is one of these. It is not a marginal puzzle at the edge of physics. It is a mystery at the very center, woven into the most basic description of matter and light, hiding inside the most precisely tested theory we have ever built. Let us draw together the full arc of what we have discovered, because the shape of it is striking. We began with a single, astonishing fact. Every electron in the universe carries exactly the same charge, identical to extraordinary precision, everywhere and always. We asked what that charge is, and found that it is the strength of the electron's coupling to the electromagnetic field, the handle by which the field grips the particle, not a substance the electron contains. We watched that single fixed property reach out into the world and build almost everything we know, binding electrons to nuclei to form atoms, organizing the elements, driving all of chemistry and therefore all of life, flowing through wires as electricity, revealing itself as magnetism, and radiating as the light by which we see the universe, and the universe makes itself known to us. Then we pressed inward, seeking the origin of this all-important property, and found a series of doors that opened only onto deeper mystery. The electron has no internal structure, no smaller pieces from which its charge could be assembled. It is a true point, and its charge is intrinsic, a bedrock feature with nothing beneath it. Charge comes in identical, indivisible, quantized packets, and we cannot explain why. Every electron carries exactly the same packet, and we cannot explain the perfect uniformity. The electron's charge matches the proton's to staggering precision, despite the two being utterly different particles, and we cannot explain the match. And finally, we saw that our greatest theory of charge describes its behavior flawlessly, while taking its value as an unexplained input. That the elegant principle of gauge symmetry organizes electromagnetic interactions without providing a mechanical source for the charge itself, and that even the famous fine structure constant, which captures the strength of it all, is a number we can only measure and never, so far, derive. What emerges from all of this is a portrait of one of the most remarkable situations in all of science. Electric charge is, simultaneously, among the most precisely measured quantities in the history of physics, and among the least fundamentally explained. We know its value to extraordinary accuracy. We know its behavior to 11 decimal places. We have built our entire civilization on our mastery of its consequences, and we do not know where it comes from, why it has the value it has, or what, at the deepest level, it truly is. That combination, perfect precision of description married to complete absence of explanation, is rare and profound, and it is the true face of the electron's charge. There is, I think, something wonderful in this, rather than something merely frustrating. It tells us that even the most familiar things, the things we learned about as children and long ago stopped wondering at, can hide depths we have not reached. The electron flows through every wire in your home. It lights every screen, carries every signal, binds together every atom of your body. It is perhaps the most thoroughly tamed entity in all of physics. And yet, it still keeps a secret. It carries a charge whose origin remains, to this day, unknown. A precise, universal, unexplained number sitting at the foundation of the physical world, governing how the most familiar particle in the universe grips the field that fills all of space. So the next time you flip a switch, or feel the warmth of sunlight on your skin, or simply look at the world and let its light enter your eyes, remember what is happening beneath the surface of that ordinary moment. Charge is at work. That single fixed property, identical in every electron everywhere, building the atoms, driving the currents, radiating the light. And remember too, that for all our staggering precision, for all the triumphs of our theories, we still cannot say why that charge is there, or where it came from. It is one of the deepest open questions in physics, hiding in the most ordinary place imaginable, inside the spark of electricity, inside the glow of every light, inside the very particle that makes the modern world run. We have measured it better than almost anything. We have explained it not at all. And in that gap between knowing and understanding lies one of the quiet, enduring mysteries at the heart of reality.